The second temperature sensor is RTD. RTD is stand for Resistive Temperature Detector. So again, it also use the concept of resistor transducer, which is when the temperature change, the resistance in the metal will also change. So if we compare with thermistor, the only difference for both temperature sensor is in terms of material. So for RTD, the material is metal, but for thermistor, it is semiconductor material. So for RTD, we can see that the electrical resistance in the RTD will change due to the change of metal temperature. So the relationship between temperature and resistance in RTD is when the temperature increase, the resistance will also decrease. So means that it has a linear relationship. So this equation describe the relationship between resistance and temperature. So you can see here, this is the resistance for the temperature that we measured. R0 is resistance at the temperature reference. 1 plus alpha is the temperature coefficient of the resistance. And it also depends on the type of metal used as the RTD. Then we have delta T. Delta T is the difference between temperature of the measured temperature and also the reference or ambient. So we can write delta T equal to T minus T naught. T naught is our reference temperature. So again, when we plot the equation, we can see that the resistance change linearly with the temperature. As the temperature increase, we can see that the resistance value is also increasing. So we in this figure, we have two types of metal material, which is nickel and platinum. So both of that exhibit a linear relationship in terms of temperature and resistance. So the common material for RTD is platinum, nickel, copper, balco, and tungsten. This is the characteristic for RTD. So let's compare between RTD and thermistor. So the first one is in terms of sensitivity. So for thermistor, we said that the sensitivity is big in terms of 1 kilo ohm per degree C. But the sensitivity for the RTD is quite small. So the sensitivity in RTD is denoted by the value of alpha. So here we can see for platinum, it is 0.04 per degree C. For nickel, it is 0.05 per degree C. Meaning, if the temperature is increasing by 1 degree Celsius, the resistance value is only increasing by 0.04, which is around 4 milliohm. Okay, for nickel, 5 milliohm per degree C. As compared to thermistor, 1 kilo ohm per degree C. So the sensitivity for thermistor is big, the sensitivity for RTD is small. In terms of operational temperature range, okay, for platinum, it is between 100 degrees C to 650 degrees C. And for nickel, it is 180 to 300 degrees C. So it's quite a high temperature there. The range is bigger than it is for high temperature. In terms of response time, we consider the response time for the RTD is slow, 0.5 to 5 seconds or more. So this is due to the thermal conductivity. Okay, so this is the design for RTD. So this is the metal material that put into coil shape. Okay, so you can see here, put into coil shape. As general, the temperature range for RTD is between minus 200 degrees C to 850 degrees C. So quite wide range because it depends on the type of metal used in the RTD. So to summarize, the advantage of RTD is it is immune to electrical noise, suitable for industrial environments, stable. The output is linear and accurate. In terms of disadvantage, it is expensive as compared to the thermistor, and also the voltage output is very small. So therefore, we need to have a bridge circuit in order to convert resistance value to voltage and also to amplify the readings. So as we can see here, we have bridge circuit here, and then the function of bridge circuit is to convert, and then the output from the bridge circuit is sent to the differential amplifier to amplify the signal. Okay, here we can see we have compensation lines. So this is due to the wire here is also having a load on resistance. So in order to compensate that load or resistance, we need to have compensation line, which means same wire will have a same resistance. So therefore, with correct configuration, we'll be able to compensate the resistance due to the load in wire. In resistive transducer, we have to consider a phenomena which is called self-heating. This self-heating occurs due to the power that have been dissipated from the device. It means that the RTD has a temperature increase by itself. Due to this, it will cause an error in sensors reading. Power that been dissipated can be calculated using this equation. It depends on the current and resistance value. By keeping the current low and constant, we can avoid self-heating. So, what is dissipation constant? Dissipation constant is a material characteristic that explains how much power required to raise RTD by 1 degree Celsius. For example, if the dissipation constant for the RTD is 25 milliwatt per degree C, it means that the RTD has to lose power around 25 milliwatt so that the temperature of the RTD will be increased by 1 degree Celsius. So, to calculate how much the RTD has self-heat itself, we can use this equation, where P is our power losses in the RTD and PD is the dissipation constant of the RTD. This value can be found in manufacturer specification.